Okay, so let's have a mass here. On this mass, this is some distance which we will call B1. There is a force here which we will call Px. There is a force here which we will call Py. There is a force here which is minus Kx. Sorry, the direction is already shown, so it is not minus, it is just Kx. And plus Cx dot, and there is a normal force here, N. This is free body diagram 1, and it gives us only linear momentum balance, only a scalar equation, no angular momentum balance, because we are not tracking the location of this N, so we don't have moment information, and it does not rotate. And we have M, that this mass is M. So mx double dot is equal to minus Kx minus Cx dot plus Px. This is one equation. All right. Now let us look at some kinematics. So let me separate this out. We are looking at this kinematics here. This point here is P. So here is the point P, and this is R, that is theta, this is L, that is phi, that is also phi, and there is a slider over here which we are tracking. Okay, so it is clear that R sine theta is equal to L sine phi. So phi is equal to sine inverse of R by L sine theta. If theta is given to us numerically, we can find phi. Okay. Of course, there is another kinematic thing to write. Our loop equation is, this is S, and in complex notation we write S is equal to R e to the power I theta plus L e to the power minus I phi. Okay, and the imaginary part of that is exactly this, and the real part of that will give us the cosine expressions that we could otherwise have written, but we will work with this. This equation gives us S dot is equal to I R e to the power I theta, theta dot minus I L e to the power minus I phi, phi dot. Okay, this equation here, which I will put in a red box, its imaginary part will give me phi dot in terms of theta, theta dot, and its real part will give me S dot, which won't need, but we could use it if we needed it. Okay, very good. But now I will differentiate this again, and when I differentiate this again, then I will get S double dot is equal to minus R e to the I theta, theta dot square plus I R e to the I theta, theta double dot plus L e to the power, no wait, minus minus I square, this is still minus, okay, minus minus I times minus I is just I square, that's minus L e to the power minus I phi but then minus I phi dot. So phi dot square plus minus I L e to the power minus I phi double dot. I should not be confused about such a simple thing, but I seem confused. It's a bit late at night. Let me just make sure I'm not making a mistake. Okay, so this is what I am differentiating. When I differentiate this part, I get a minus I and a phi dot. That phi dot is phi dot square. The minus I times the minus I is I square. That's minus 1. That's what it seems like to me. Okay, if I've made a mistake, please let me know. Very odd. Okay, so now over here, the imaginary part will give me phi double dot in terms of theta, in terms of phi, which we have found, in terms of theta dot, in terms of phi dot, which we have found. S double dot will not be needed, so it will give me phi double dot. Okay, and it will also, S double dot will also come out. The real part will give me S double dot. And now my kinematic analysis is over. All right, I will now move here and use yellow again. Now I have to do equivalent masses. So I have this circular thing. Its center is at P. Attached to it rigidly is a rod. Over here is a mass which I'm calling MA1. Over here is a mass which I'm calling LC. This distance is R. This distance is LC. Okay, this has a mass, let's say MW, and a J. All right, now this system, I also have over here another rod, and this is MA2 and MB, and remember I have a slider which is MS. What I am going to do is I am going to transfer this point mass to the slider, and I am going to transfer this point mass over here, and then this rod will just be hinged at two ends, but it will be massless. There are no dynamic consequences. Equations become easier. So now I will write MA is equal to MA1 plus MA2. That means I have transferred this one here. And I will also write MS bar is equal to MS plus MB, which means I have transferred this one here. Okay. And now because this is massless and rigid and hinged at two ends, this is a 2-force body, which you will remember from trusses. Okay, all right. Now let us look at this body again. Let's look at it using green. So here is the body. Maybe we'll do it here. So here is the body. Here is MA. This distance is R. This is LC, MC, MW, J. This body will now have a new center of mass, which is located at G. Okay, and this distance is something, we have to give it a name. Let us call it H. Okay, all right. This body has a new mass, Mnew is equal to MA plus MC plus MW, no problem. Okay, it also has a location H. H into Mnew is equal to MA into R minus MC into LC plus 0 times MW, which I'm not writing, and this gives me H. Okay, so I've located the center of mass. it also has a Jnew, which is equal to the moment of inertia of this by using parallel axis theorem, that is J plus mw h square. Remember, I found h already, there's no problem, plus ma times r minus h square plus mc times lc plus h square. So I've got my Jnew. The angular velocity of this body is equal to theta dot. That also I know. Okay, let's see if there is any space here. Not much space. What I will do is I will come back here. Now I'll draw a free body diagram of this. Body. Remember, this is the point P. Over here there is a force Px and a force Py. Over here there is a force F. Remember that this angle is phi, and the center of mass of the body is here at G. Therefore, I need to find the acceleration of G. To do that, what I do is I write Rg, again complex notation, Rg is equal to x plus, remember this distance here, this distance here is b1. Okay, so Rg is x plus b1 plus h e to the power I theta. That's Rg. Okay, remember, complex means this is effectively vector in 2D. All right, good. So velocity of G is equal to x dot, that's 0, plus I h e to the I theta dot. The acceleration of G is equal to x double dot minus h e to the I theta dot square plus I h e to the I theta double dot. Okay, good. So we are not introducing any new unknowns. Okay, these are our unknowns. Ag is what it is. You have to rearrange your equations as you wish, but that's what Ag is. And our linear momentum balance now, LMB, is equal to like this. Minus Px minus Ipy minus f e to the power I with a minus phi. If it was like this, it would be, if it was like this, it would be e to the power minus I phi. Now it is the opposite, minus f. This is equal to m nu times a g. This has a real part and it has an imaginary part, so it's actually two equations, and you have to separate those out. We have done these exercises before in earlier homework. Okay, the cross product is a little harder, so we have to do it. The cross product comes from this term, and this term, the angular momentum balance equation, but the way it is written, it is easy for you to write, so I will not write the whole thing again. This force is at an angle phi, this is at an angle theta. You have to sort out the perpendicularness. You just take a vertical component here and a horizontal component here, just write out the moment equation directly. Otherwise, as one of the students in the class had shown, there are some other ways of doing it, but you just take moment about G counterclockwise from those forces is equal to J theta double dot, and that is another equation. Okay, so here we have px py f x double dot theta double dot. So actually I have 5 unknowns. I have px py f theta double dot x double dot, and over here I have 1 2 3 4 equations so far, 1 equation left, and that's really easy. That's not a problem. That last equation is from this free body diagram. Over here there is a force, that is F. This angle is phi. There is some normal reaction which we will call M1, and so it is easiest to write F cosine phi. Remember, phi we know is equal to m bar s times x double dot plus s double dot, and that is our fifth equation. So we can solve for everything. Now in MATLAB, what do? Just we do ODE 45. For that we have to give it an M file. And what is this M file? It is a box. Inside this we send time t, which we don't use, and we send the vector theta dot x dot, and it returns theta dot, which of course it just shifts it over, it knows that, theta double dot x double dot. That's what it returns. Internally it solves all these equations, this one, it finds all these variables internally, but it doesn't matter. What it returns is this, and then ODE 45 gives you the solution. That's all you need to give ODE 45. Thank you.